recording. I gotta share application, smartboard.
What's up? Need a bit of help with some stuff.
Sounds good. Came to the right place. Alright, you know which problem specifically?
17.
I'm just confused for me, I'm just confused on a particular process.
Okay. You know what it is?
I can't remember what it's called, but it's on the not WebAssign, Sapling.
Okay.
Which is why I brought my big giant machine out, because it's the only one I have.
Alright. So this one, following equations balance combustion reaction for C6 H6. Okay, if you have that many grams of that is burning, heat is produced. You guys all understand that O2 as a reactant is just burning? Yes?
O2 is burning?
Or like when you have a reaction and then you have O2 in the reactant side, it means the thing is burning.
Yeah.
Okay, good. Just want to make that clear. Just so you guys know, just for future reference. Heat produced, is added to that much of water.
The more appropriate term is oxidizing, with burning just very, very rapid oxidation.
Exactly. Alright, so first you have to find the amount of heat produced by burning the C6.
Yeah.
Did you figure that out?
No.
Okay.
I wasn't trying to get that from the stuff.
Okay, so everything right now is I'll just write down the problem for you. So it's 2 H6. Wow. Okay. That just like went down for a little. Make sure you guys pass around the sign-up sheets to make sure everybody.
I need to do that too. So that I get extra credits.
Who you? You guys
I
have
think at least that's what it is for my math class. Whenever
you guys come to these sessions, you guys get extra credit.
I think you get extra credit. Only very minor extra credit though. Probably like 1 point or something. I don't know.
Oh, advantage too small.
True. All the points.
I guess it's like sort of like a little incentive per se to come to SI tutoring.
Main reason why is because majority of like incoming like first years, they always think like, oh, I don't need any help, I don't need any tutoring. It's like, really not really need it. I don't really need it because I'm smart and I don't need it, right? But you come to realize that going to like these sessions or going to the ARC especially, that helps out like a whole bunch, and it can really make a difference on your grade.
Well, depending on your schedule and which you're free and which
The ARC is really.
the ARC is good.
Really
Whenever you could find a time when there aren't too many people.
Yeah.
When there are a lot of people, it's not particularly useful.
Okay, so you have to first find the heat produced by burning the given amount of that compound. So what does yours specifically say? I'm going to use what?
I don't know. Yeah, just do your numbers, then I'll do it later.
So I have this much grams of C6H6. Okay. So basically from here it's just basic stoichiometry. That's what that really.
Oh, are we trying to find how many grams?
How many joules?
You're trying to figure out.
Oh.
No, what? 17? It says what is the final temperature of the water?
Oh, the final temperature.
Eventually, right, but
Oh.
we need to find the heat produced first. And then
Yeah. Okay, so basically it's just simple stoichiometry from here. So, how many moles?
This is bomb calorimetry, correct? It's bomb calorimetry.
This is just a combustion reaction. I mean,
That's what it's called.
Yeah, but okay, so from here, what is the format?
It's 12.01 times 6 plus 1.08 times 6.
Yes. So.
Okay.
78.
78.114.
1 1. I'll split it at 1 1. All right. So this is that many grams of that compound.
All right.
Yeah.
You guys
You guys are all here. Cool. I haven't seen you guys in a long time.
Well, it is the season
Okay.
for spooky.
So basically, that is converting moles. Right? Based off of the equation, you know that for every 2 moles, it produces that much. Right? So from here, you basically just do 2 moles of that specific compound for every 6,542 kilojoules. Right? Alright, so basically from here you get some arbitrary number. Okay. And obviously you can change that to joules if you need to. I think you actually might need to. Yeah, definitely need to. So you guys have learned the rule of Q equals MCAT, right?
Q equals MCAT.
Yeah. You guys haven't learned that?
That's copy of calorimetry.
Yeah, you definitely risk know that for this problem.
Okay.
Q
Oh,
equals
yeah, yeah.
MC delta T. I call it MCAT because
Oh,
Yeah.
yeah. MC delta T.
it looks like MCAT. So that's what I've been calling it since like high school. So from here, you're basically doing that one. Okay. This is a very, very big concept. You guys are gonna need to know that basically on all of your exams and stuff.
See, now you made me write cat.
Oh really?
Well, I guess it's a good way of memorizing it.
Yeah. No, that's how I memorize it. You guys probably gonna tell yourselves like during class like MTC. Okay, so basically from here, how would you solve for, because you want to figure out the final temperature of the water, okay? So how would you rewrite this in just so temperature is by itself?
Where it is.
Changing T equal, or do we want the final temperature?
But yeah, I mean, so you're going to do temperature equals what?
Q over M.
MC.
Cool. Yeah. So from here, just make sure that you know that heat
Q heat is
it's in terms of joules, okay?
Right.
So whatever value you get there is going to be kilojoules, so you're obviously going to have to do what to it for joules?
Divide or multiply by 1,000.
Exactly, multiply by 1,000, so you get joules. And plug and chug, and you get a specific temperature. So from this value, you actually want to work out this problem. This one says that the value eventually becomes to be 15.65 degrees Celsius. Okay. And then from there, you basically
Could you scroll up a bit?
Oh, sorry. Right, how
It's
far?
like, yeah, that's fine.
Perfect. Okay. Okay. And so this M right here is basically going to be the, this is going to be the mass of the water that is given to you. Okay. And then C is basically just going to be, that's just a constant, right? C is constant? Yeah. And then your C value is what? 4.1, something like 4.184, something like that. And then Q, solve for delta T. You eventually get your delta T value to be somewhere around that, depending upon how many grams you start off with. Actually, change actually is always going to do that. And then, are you guys good? Sure, yes, okay. So basically from here, you know that the temperature final is basically going to equal T initial plus change in temperature, right? This is rearranging temperature equals, yeah, basically. So basically from that, you solve your answer in degrees Celsius. And that's your answer for the problem. Cool. Awesome.
I can't see.
Oh, my bad. Picture. Oh. Did you guys pass around the sign up sheet? Yes?
Yeah.
Yes? It's only right there? Cool. All right. I'll pick it up later. Do you guys have questions on this? This is
What number is that?
this is number 17 on Sapling. 17 on Sapling, yes. This is just to help you guys, because you had a question on like how to do it. So, yeah. So basically, this is just like how you guys would approach this problem. There's gonna be a lot of problems that are kind of set up like this. It's a lot of just plug and chug and just kind of figure out what values you need. A really huge trick to this is basically just using stoichiometry.
TE.
It's never gonna go away.
Term of joules. Okay.
What's up?
Nothing.
Trying to take a picture.
That was good. That was good. Awesome. So,
Okay.
do you have any questions on it?
Yeah, no, I have a question on a different one.
Okay. What question?
Number 10.
Number 10. Okay, so researcher studied the nutritional value of a new candy piece. Interesting. Candy inside a box. Oh, okay. Observed temperature increases with that. Heat capacity is that. How many nutritional calories are there per gram of the candy? Interesting. Very interesting.
I got it wrong 4 times.
Oh shoot. All right. Let me just got this. This is at constant pressure, so that's gonna be a huge giveaway. Constant pressure.
Mm-hmm.
Yes. That's good.
So Q is 10.
What's up? Basically, the heat of the reaction is basically really, really close to delta U.
6, 5, 4.
Delta U.
Yes. It's very, very close. You can assume that because it's constant pressure and constant volume actually. Yeah. Okay. So basically from here, let me scroll down. Okay. Alright, so this guy is number 10. This problem actually ends up being not too bad. Question.
Shut up.
That's what my roommate says all the time. Okay.
I told you to shut up when you sneeze.
Yeah, he does it all the time. Does it all the time. It's ridiculous. All right, so basically you got Q is going to be equal the heat capacity of the right? Yeah. So that's C, and then it's just delta T. Right?
That's the heat capacity of the cal. That's the calorie. That's the heat of the calorimeter.
Yeah.
Okay.
And then we're just trying to use to solve for it.
Yeah.
So basically, you just use this formula. Okay, so for temperature, you don't really, even though it says like the temperature increases by 2 degrees Celsius.
Mm-hmm.
In this case, the fact that it says that the temperature is increasing, you don't have to change it to Kelvins.
Mm-hmm.
Main reason why is because the difference between 1 and 3 is the same as 11 and 13, right? Same concept. So basically, the change in temperature, you can just leave it as whatever value it is, which is 2.51. It might be different. My promise is 2.51. Yours might be a little bit different.
2.13.
Okay, yeah. So it's gonna be a little bit different. But basically, from that's your change in temperature, and you take C times that value to get your Q. So from Q, that's going to be measured in kilojoules. So your Q, I'm going to put this in parentheses because in kilojoules is basically, you're just going to do another stoic problem, and essentially, because they're asking how many nutritional calories are there per gram of the candy. So you want to try to figure out how many calories are there. And they give you the heat capacity of the calorimeter. So it's basically just 1 gal over 4.184 kilojoules. Right? And then they'll give you a value, which is in calories. And then they just want to ask you, they're asking how many calories per gram, and they give you the amount of grams there are. So you basically just take this and divide it by,
Wait, that's 4.18 kilograms per calorie? A kilojoules per calorie or kilograms per calorie?
I mean, it's just inverted, so yeah, kilograms per calorie.
Seriously?
How much?
I don't get that.
It's a constant.
So 4.184 kilograms has 1 calorie.
I mean, that's basically what that is. Basically, it's just that's what's converted. Yeah. You just need to know it's the constant. I'm sure you guys are going to be given it to it on the test. Why are there so many fucking bugs? Again. Anyways, so does that make sense? Because this is you want your terms of calories per gram of candy.
Right.
Right. So this is basically going to be. I mean, yeah, you could basically just figure it out from there. I'll just put X and Y because they're variables. Cool.
And that's the answer.
That's basically the answer. Because they're asking how many nutritional calories are there per gram of candy.
Okay.
Yeah.
We'll try that.
All right. Anybody else have a question? I know you had a question about another one.
Yeah, I'm still working on that other
Can
thing.
you answer a quick question on the lab?
Yeah, sure.
Real quick. So, just wondering for this equation, are these C's, they're all for cold water? Because I feel like it should
I got it
correspond,
wrong
right?
there.
I would assume so, yeah.
Water, right, is like a type, but then for this one, is this a calorimeter?
Interesting. So, yeah, that's definitely
So this one's for sure.
yeah, I'm pretty sure that. Yeah.
Because when I was doing it, then I didn't really know how to get if that was calorimeter.
Yeah, that makes sense. So basically, is this the styrofoam cup?
Yeah.
Yeah, have fun with 50% error. You guys want a ridiculous percent error. Because even though Zion says it's such previous, it's really sucks.
Okay.
What Super is asking basically is that,
What is that? Yeah.
okay, so.
10K.
What about the Is there a back to this? Yeah, it's definitely just the calorimeter.
That's temperature of care.
That's the temperature of the calorimeter.
How do you find that? I was having trouble with this stuff.
I got it wrong.
Oh, there.
Yeah, 1 divided by 4.184. Yeah.
No, the answer is not 1 divided by. The answer is not 1 divided by that value.
Still not understanding.
Okay, so Q equals C delta T. I'm pretty sure. Let me get back to you. Hold on. So Q equals C delta T. So you have your. How do you solve for Q? Your Q value is basically the heat capacity of the calorimeter, which is what?
Oh, Q is the heat capacity of the calorimeter?
No, C is.
Yeah, C is 47.80.
Okay, so you multiply that by the change of temperature, which is
2.13.
okay. So take those two, multiply them together.
Okay, 2.13
So
times 47.80.
Yeah.
It is 101.814.
Okay. So that's how many kilojoules, and you want to find the amount of calories from those kilojoules. So you take that value, kilojoules, and divide it by 4.184 to get the X amount of calories.
So
But if
our
it's
Q is
cold, you
just the.
multiply by how?
No, because 4.184 kilojoules is 1 calorie.
No, this is the conversion. Oh wait, shoot, that's not kilograms, that's kilojoules. My bad. That's probably what's screwing you guys up.
Yeah, that's
Kilojoules, my bad.
don't be.
Oh. Wait, why are you doing 1,000 calories?
Because it's capitalized, so it's a kilocalorie. We're solving for kilocalories.
That's a
See?
kilocalorie is a calorie capital C.
Yeah.
Oh, then don't understand with the 1,000. It's already in terms of kilojoules.
If I thought 4.184 kilojoules had
For
1 calorie.
1 calorie.
Is it a lowercase c or uppercase c?
Uppercase C.
C times
don't do any.
delta
All you
T.
have to do is plug in numbers and then just go through it.
C times delta T, which is
So
2.37.
did you ask for the? Are you not trying to solve for it?
Well, I am. I'm trying to find K constant.
To solve for K,
Yeah.
you need to know the change in temperature. I would assume, okay, so the change in temperature of the cold, so you guys basically, what you guys do? Tell me like what you guys do.
We have cold water, and then we heat up some water, and then we add the hot water. To measure the temperature. Basically it.
I guess the change in temperature in that system right there is basically Delta calendar.
It's just,
It's basically, change temperature of the calendar is basically just change the temperature of the full entire system. So I would assume that it's just, I mean, there's not really,
and then is it the change of the warm water and cold water?
how are they different? Because one went from, so, change temperature of the cold and change of the warm. Oh,
Yeah, the first stage.
yeah, there are different values. Oh, sweet. Okay.
So this one goes from the cold water, it's like from like 80 to 30.
So 30, and then went from
The hot water goes from 3 to 73.
That's a very good question.
But I don't know either of these yet.
Yeah. Okay, thus, if the temperatures of one water, water, and the water after mixing are known, and the mass of water, cold water, specific heat capacity of warm water, cold water is almost the same. Yeah. Okay.
4.1.
Yeah. Yeah. Thus, if the temperatures of cold, of the warm and cold water and water after mixing are known.
Yeah, we know all the time.
I mean, it's kind of a stretch, but I would probably just take the average of two.
So that's,
Change.
And that's if you're only running like a really think of.
9.91.
It definitely can't be zero. Because, there must be some sort of-
Right. It should be really small,
Yeah,
hopefully.
I
But
hope so. So the flow dynamics, the energy change in an isolated system is zero. If you mix a known quantity of water with a known quantity of water, there's no being transferred to the surroundings. Heat lost by the zone plus the gain of that and the parameter must be zero.
So,
Since the heat is flowing out of the warm water, the QC and Q cal will be positive since heat is flowing into the cold water.
so the heat from the hot water.
I would
equals
assume we
water
actually use the cold water.
Just use cold water.
Just use the cold water. I mean, one, it makes sense to just use the cold water because it's also a positive value, and also here they denote it as C rather than CAL, which would be calculated. So I guess just use the.
Alright.
If they.
I just wasn't sure. So.
No, yeah, no, I got you.
Thumbs up.
Thank you.
Yep.
Question number 11. Yeah, I did.
There you go.
I didn't get, why not get 5?
Wait, what's up?
It's,
What's up?
why is number 5 not, because I'm doing this, what,
Roll from math.
I would use my calculator, but I don't have it and it's not charged, so.
This is number what? Number 5.
Number 10.
Oh, number 10. Oh, which is the problem we just did.
And,
I think you're off by.
Sure, yes.
Okay, so what did you do?
so that's pretty much what I did.
So you took, what's your C? Where's your C?
C is this
Okay, and you multiply it by this.
4.184 times that, and then they can get you this
Okay, and you divide it by that to get that value.
2.36, which you divide by 3.50.
You couldn't calculate it yourself?
Wasn't, I don't know why your values. Did you like calculate it?
Yeah, because 9.91 times 1 over 4.0.67,
This is your value.
which is that, essentially.
That's good.
Grams.
Oh,
Do you know how
you're not
to-
multiplying it by that. You're multiplying it by the heat capacity of the calorimeter, which is that value.
1 mole of C.
That's supposed to be heat capacity.
Yes. I think. Yeah, no problem. That's why it's wrong.
Okay, now I know it's wrong. Can I get some?
Which one?
6
Let me just write that,
all over how many grams you have of that.
because I'll fix that later, because this has really been what's plaguing me with all this incompleteness. I do not know.
Number 11.
Generally, any problem involving the standard enthalpies of formation, what is the reaction? And I go, and it's like, oh, use this table to find the stuff. What is this? What? I don't even know how to use this big giant table of stuff.
You basically just look up the individual individual components.
But the thing is, in some of them, the individual components aren't on the chart.
No, they should be. They definitely are.
It's like CO.
I'll just write them down for
There's
you.
an actual.
I'll write down the ones you need so you don't have to look them up. Alright.
Like, I can't find CO on this chart.
Should definitely be there.
Oh, carbon and oxygen are individual things. But it should still show. And am I supposed to just add up all the enthalpies of reaction?
Yeah, you just basically just add up the products and then minus the reaction.
Oh, CO2 is that divided by 2 gets you CO. Wow.
Wait, why would you divide it by 2?
Because it's CO, gas, plus H2O, not CO2.
No, that's not the same. They all have different delta H's. You can't just simply just have it because it's CO2, CO.
How could I figure out the standard enthalpy of CO?
It's given to you.
That's, do control F. CO.
I like those. I like these items.
CO is not on this chart. Oh wait, what? There it is.
Definitely should
Hidden
be on.
amongst everything else.
Should definitely be on there.
Okay.
Alright, so basically,
All right.
does that make sense then?
Yeah, I'll do one, just make sure I understand.
I
that
think you got it.
understand.
I think you got it. Alright.
And then I'll ask a question about something else.
Okay. Alright, so did you have a question?
Yeah. Number 11.
Number 11. Okay, how did you approach this problem?
Well, I find the heat capacity of the calorimeter, and then I found delta T. The heat capacity of the calorimeter is 1.589 kilojoules times Kelvin to the negative 1.
Okay.
And delta T is 0.470.
Okay.
So, like, to that negative 1, do I apply it to the actual number, or is it just a unit?
The k to the negative 1?
Yeah,
That's prep units.
or it's just a unit, so I just leave the number by itself, I don't
Yeah,
put
you
it
just
in.
leave the number by itself.
Is that
Essentially, like, well, my value is this. You know how I would say, shoot, this would say kilojoules times k to the negative 1.
Mm-hmm.
Essentially, what that means is 1.08 or 89. It'd just be kilojoules per k. That's basically what that means. Same thing. It's just a unit thing, so you don't have to worry about it.
Can we just do it that way? Because that thing is throwing me off.
Just know that that's just how I mean, I would assume the main reason why is because they're typing it, so it's kind of hard for them to write fractions.
Mm-hmm.
So that's basically what that means. Does that answer how to solve this
Yeah,
problem?
and then, you're on number 11, right?
Yes.
Okay, so I found the Q of the calorimeter.
Yeah.
So I'm trying to find the molar heat of solution. Wouldn't it be wouldn't it be the heat of reaction over a number of moles? The Q of the solution, right?
Yeah.
And that is
Yeah, actually, that's exactly right.
Equals heat of reaction.
But make sure you have to use it for the heat of solution. It's the heat of the system. Heat of the system divided by the moles.
Q of the system divided by moles.
The H of the system, delta H of the system. Because essentially what you should be initially solving is trying to figure out what's the delta H of the surrounding.
Mm-hmm.
Right? So that's basically just your total heat capacity multiplied your change.
So the calorimeter is surrounding.
Sorry?
Is the calorimeter the surroundings? Or is it the system?
Using the total heat capacity. Dissolving water in a calorimeter that has a total heat capacity of that. So I guess that's your surroundings.
So the calorimeter is the surroundings.
difference.
So that means the system has an opposite sign.
Exactly. So the fact that the temperature is deep negative value, but the delta H of the system is going to be a positive value.
Right.
Right. So this is going to be a negative value. So that means your delta H of the system will be a positive value. And whatever positive value you get, you're going to basically divide that by the number of moles of, I would assume, is it KCN? So
Yeah, Kate. Yeah.
So basically, you have to use the amount of KCN that you have and do stoichiometry moles of that. Then you just do basically delta H of the system, the number of moles of KCN to get your answer. And your answer is just obviously just going to be kilojoules per mole.
Right.
And this is delta H of solution. Any other questions?
I have two more.
More? I just want to let everybody else see what they have. Do you guys have any other questions? Or you guys just tagging along? Just checking it out.
I have a question. They're later on.
Okay.
Okay, good.
What's up?
I have a question.
On the test. Okay. More specific.
Oh, I was so pissed off. I understand why I got that low grade. Because you know the test, because they had the like on the two ends, it's like the big old glass bulb with the skin.
With the valve?
Yeah, so I had solved the first page. Then I went to the next page, and I thought the next page was about a totally different problem.
Oh.
So, because I didn't know that they were connected together. So I was kind of confused, and I lost.
Yeah, I asked the guy that was passing by. He's like, "Oh, I don't know. I just passed him out."
It was practically, that was like 14 points down the journey, basically. If I had gained those 14 points, I would have gotten an 83 or 84 out of 100.
Hey.
I know, right?
I got a 50.
So basically, you did well. You just missed that one thing.
Yeah.
Well, now you know what to do for the next time.
That sucks.
It does suck.
Because I was like, am I the only one that thought this? It was like
No, man.
almost 87.
Same boat as you, man.
Definitely have to watch out for those because multiple problems. Okay.
I just hate multiple problems.
Realistically, all of his problems are actually, I would call them kind of easy because what he does is
He builds off.
he basically starts off a problem and then gives you another question, which is basically the next step of that problem. So he's basically asking you questions about, like, if I were to like do a whole entire problem and I'd get an answer, that'd be worth like 14 points, right?
Right.
But he would ask a question here, and each checkpoint would be worth like 2 points. So basically, that's what he does with his tests. That's why he makes it like 2 pages long for one problem.
Right?
Right?
I'm totally screwed up.
That's okay. But now you know. Now you know. Okay.
Final.
But you guys still have one more exam.
Oh, this one's her?
Yeah, you guys have exam 3, and then you guys have the final. And it's like really close to each other. It's like, I think he said that he's gonna give you guys the exam 3. He was talking to me about it because you're like cross paths. He's talking to me about you guys probably taking the
third exam before Thanksgiving break.
Gosh. We should be grateful for that because after Thanksgiving break, not fun because you literally don't want to do anything over Thanksgiving break. And then literally it's like a week or two afterwards. It's like fine. Yeah. So
Moral of the story: spend less time on the turkey and more time on the.
well, I mean, in this
Study
case, if he
material.
puts it before the Thanksgiving, then you guys can have as much turkeys.
Well, for the final.
True, that's true for the bottom. All right, what problem? Or what question? Your both of these?
Yeah.
Moles of pH. Oh, that is neutralized in the titration. Okay, so that's from here, right? So you got that right. So this how many moles neutralized. So this how many moles of HCl. 32 moles. Oh, because O2 has two next to it. This is only BaO. This would be right if this was written as BaO2 or OH2. Does that make sense? Because this, you're saying that you're saying 2 moles of this equals 1 mole of this whole thing. And there are 2 moles for every one of these whole things. So basically you do 2 moles of HCl for 1 mole of barium hydroxide. And then 1 barium hydroxide, you have 2 moles of H or OH. So basically, I believe it actually would be the same value. These 2 things. And the reason why they're the same is because this thing produces water, which is, they should be giving you about pH, which is something, which should be neutral. Because this is essentially what this reaction is. So, yeah. Okay, does that make sense? And that's why that affected this. But this didn't. This wasn't affected by these 2 because he just used these 2 values that he came up with, and he used it for this. So he was like, if you got this wrong, then you get this and this wrong. But the fact that that's why you only get minus 2 instead of the full minus 3. Because you just missed that small word. Okay. All right. What other questions do you guys have?
Me.
Yeah.
I'm still stuck on this one problem. So 11.
So 11.
Yeah. I don't know why.
Okay, so the delta H of the surrounding. What did you get for that?
I got.
Or how did you figure it out?
Okay, I got C and delta T. Zach was telling me that delta T is negative because the temperature decreased.
Yeah.
So I got negative 0.470 times 1.89
Okay.
equals negative 0.747.
Okay. And
So
what's
that's
the delta system.
That's just positive 0.747. So then I got the heat of the system. So then moles is 3 grams times 1 mole over 97.181.
97. How'd you get 97?
Wait, is that KSCN?
KCM.
KSCN, that's the molar mass.
It's just KCM.
KCN? I got KSCN.
What's your compound?
KSCN.
Okay. Yeah.
Okay, KSCN. K.
So what you get your molar mass to be?
Molar mass is 97.181.
Hey, how many moles?
So it's 3 divided by 97.
Yeah.
181.
Okay.
3 divided by 97.181, which is 0.03.
Okay.
So that's 0.03 moles. So I got the heat of the system, which is 0.747, divided by 0.030.
And divide that, what you got?
I got 24.9.
Are you using enough sig figs? Because you're kind of work a little bit. So,
And I put it in there and it said I'm getting it wrong.
what is your? So you did. So your heat capacity was what?
Heat capacity is 1.589.
Okay, and you did that multiplied by the change in temperature, which is
Negative 0.470.
470. Cool. Okay, so you got negative 0.4 or 74683. 683. Okay. 683. And you multiply that by negative 1, so that would be the change in the delta H. Okay. And you used 3. Here, I'll store that. So you had 3 grams, right?
Mm-hmm.
So you had 3 grams, and you divide that by the molar mass. What's the molar mass?
Mm-hmm.
97.181. And that's how many moles.
Mm-hmm.
So basically just take X, whatever your math is, like that. I got this.
24.19?
What did you get?
I was 24.9 exactly.
This should be right.
I got 270s.
That's okay. Just so you know, actually, we're advice for all of you guys. When you guys are solving out problems and you don't know like about sig figs, specifically for sapling and also having to guess for the test as well, try to keep as many decimal places as you guys can. This without rounding in between the problem.
Oh,
Because if you guys do, you guys are going to get a slightly different answer.
I could have. I'm so pissed off with the test, man.
Hey, at least you know that you thought you did well and you actually did do well, right? But obviously the grade didn't reflect it because of that one minor hiccup,
Yeah.
right? So I mean, nothing to be too bummed about. As long as you know all the material, that's good. And the finals was what, 20% of the grade?
Yeah. Hey, I'm also kind of happy because in comparison to other people, I scored quite well.
Oh, there you go.
It's kind of sad.
Don't worry, my friend's organic chemistry class is average. The average of the class is an F.
Wow. Is what?
The average of the class is an F. That's how hard it is.
Well, did you take the class?
No, I'm going to next year. So like a year from now.
Brace yourself.
Oh, I will. All right. Any other questions? This is about your test. Okay. Let me hold up on that. What was your question?
My question was on number 15.
Number 15. Okay.
It's another enthalpy.
Another enthalpy one. You get skipped that one. Oh, this one was fun. Oh, whoa. Wow. Okay. All right. Okay, so produce carbon dioxide. Blah, blah. Cool. Do reaction. Awesome. So basically, you're trying to solve for what? To calculate the number of moles of CO2 produced per megajoule of heat released from the combustion. Okay. So, just so you know, there's 1,000 kilojoules per megajoule, right? You know that?
Yeah.
Okay, good. So
I'm just not sure how to
okay.
go about doing this sort of problem.
So number 15. Basically, the first one's coal for you, right?
Yeah.
You have coal? Okay.
Coal, graphite.
Is basically C, which is graphite. Graphite. Cool. So the reaction for this is basically just C, which is the solid, which is graphite, because there's a lot of different carbon solids. And then you're basically burning it, which is O2, which is going to produce CO2 gas. Right? So basically from this reaction, you just go through the delta H, heat of formation table, and then you just plug and chug and you figure out what the delta H of the reaction is. Okay? And then once you get that value though, you know that this is the amount of kilojoules per mole.
You want megajoules.
Exactly.
So multiply whatever you get by, no, divide it by 1,000.
Yes. Yeah, essentially. You divide it by 1,000. Why did they get such a weird answer? That doesn't make any sense. That makes sense to you though?
Yeah.
Okay. So that's that, guys, for A. And then
Same thing would be,
natural gas.
yep, pretty much the same thing. And same thing kind of with C.
Natural gas.
This does involve some balancing.
Yeah. So you have CH4 gas plus 2O2 gas, which produces CO2 gas plus 2H2O liquid. And then from that, you basically do the same thing. Yeah.
Two CO2.
That's just the balance of it.
Two O2s, I thought.
2O2, because you have CO2 and then you have oxygen there. So you made this 4 and then you put that as 2, so then it would balance.
Okay.
Yep. And then for C, the propane is basically just going to be C3H8 gas plus 5O2 gas, which is going to be burned, which is going to produce 3 CO2 gas plus 4 H2O liquid. Those are sloppy. Here, just write down these formulas, and then you can basically just go back into it and then just look at the heat information. Cool.
Yeah.
All right. So this guy was for octane.
Yep.
So this guy, this one's a little bit funky. CH18, which is a liquid. Keep in mind this is a fraction because there's really, I mean, you can multiply everything by 2 if you want. You're going to get the same answer. This is just multiples of each other.
Yeah.
Cool. So that's octane. So basically use those formulas, find the delta heat of formation of each individual compound thing, and products minus reactants. Bam, figured it out. You take a picture of that.
Yeah, I'll just do that later because that will take a bit of time.
Yeah, looking up all those values.
Oh,
That's for sure.
let me
figure it out and then get put to the next step.
alright.
Okay, so calculate the root mean squared of that. So you did the root of that times r times t divided by, that's why. This is in grams. Wait, what is this? More mass? Is this more mass or what is this? Okay. Yeah, this is in grams, and it should be in kilograms.
Oh.
That's why they wrote -3 kilograms. It should be in kilograms. That's the millimeters. That's why they only give you -2. Oh shoot, did they give you minus like all of it? Do they give you minus all of it? Because there's number, is it right down here? On number 5. It's like this. On number 5, you have 7. 3, 5. Yeah, no, you only got -2 for this. I think they're just saying it's just a capacity in kilograms. That's
No.
I think so. Where did you just found it? You didn't even solve the problem.
God damn.
God damn. Wait, did you solve it?
Let it down.
Oh, from here.
Tell us your answers.
No, I put it's here.
Oh, I think they're saying because like you shouldn't use like 0.003 because helium gas is just. Yeah, I'm pretty sure it's just. I think you're right. So. Yeah. Is there anything else? This one.
Yeah.
So gas is compressed at constant temperature. That what happens to the root mean squared compared to part A. So your volume is being compressed to that. So you basically your volume decreased good, and then your pressure increased. Oh, but well, if you have, okay, think about it this way. Everything else stays the same, so temperature stays the same, molar mass will stay the same. It's just your pressure. You're using PV equals nRT. You know how PV equals PV. If I just take, so basically you could just take 1 times 1, pressure times the volume. 1 times 1 is going to equal 1, right? And then you take the pressure to the volume, 2 times a half is what?
1.
Exactly, so it would be staying the same. So nothing would really happen because it wouldn't change your other values, such as moles. It wouldn't change the amount of moles. I mean, assuming that you're using the same thing. The gas, the moles would stay the same, temperature the same. Yeah, it was just basically all stay the same. Is that the right answer? Did you check? Did they not post the answer, please? Oh, okay. I would assume it's basically stay the same. Using PV equals energy, using the laws.
Temperature change.
These are the laws it should be said. So. So basically the whole test. Okay. Let me get back to you. Do you guys have any other questions?
I do.
Yeah, what's up?
Number, the last one, 21. Actually, 22.
22.
It's a Hess's Law problem. I know how to do it, but for some reason, Sapling said that I'm incorrect.
These are the correct please. Oh, shoot. It might be 6. So I'm really stingy about it.
No, like the very first homework, they cared about 6 flicks a lot, and then all the other ones, they didn't care as much.
Don't know what to talk. So 22?
Yep. 22. So I had to do that. I had to do that.
So what? Alright.
But that should be
Oh, we've done
correct.
this before.
Yeah, I know.
We've done this before, dude.
Yeah, I know.
That
That's the
should
thing.
be correct. Why is it incorrect? That should be correct. And it's saying it's incorrect. Why is it saying it's incorrect? It's right. It's right in math.
Okay. So, are we?
How do I figure out?
Yeah, that's what I'm saying. Like, I know how to do this thing. That's
Yeah,
the
you're
thing.
gonna do it. We literally spent a whole bunch of time on this. Alright. Alright.
1.7 megajoules of energy.
So what do you do?
Okay, so I know in the first, like, okay, there's the main equation. I'll call it the main equation. Like, the first
30
equation,
joules per-
equation A, I call it, has 2 ms solid,
Yeah.
and the original equation is ms solid.
Cool.
So that particular equation, there's no change.
Okay. Cool.
Now, for number B, there's no HCl in the original equation, so I'm just going to leave that alone
Okay.
for now.
Yeah.
And then
Good.
for the third equation, for the third equation, there's 1 CO2 gas, and then there's 3 CO2
Okay.
gas. So
What?
multiply the whole thing by 3.
Yeah.
And you do not change the sign because they're both active on the side.
Okay.
For the fourth equation, there is 2 MCO3 solids on the reactants. No, there's actually one MCO3 solid on the reactant side,
Yeah.
but there's 2 on the product side
Yeah.
for the original equation. So you have to multiply that by 2. You have to flip the whole equation around,
Yeah.
and you also have to change the sign.
Yeah.
You also have to multiply the enthalpy by 2.
Okay.
But you also have to multiply the enthalpy by 3 for the third equation as well.
Yes.
So then the new equations, I saw the MS. So the MS is good. Yeah, that's pretty.
So these are your changes. So,
Mhm.
so it's like here and then here.
Yeah, I wrote it without parentheses to differentiate.
Okay. So you got that. So you took this, you multiplied by 3. Good. And then this guy you flipped and multiplied by 2. I think that might be something that you.
What happened?
You wrote change sign, but I would suggest writing it as multiplied by -2. That might help you. I think that might be,
-3. Oh.
that might be a change up.
Oh, I think I know why. That may be it.
That's I would assume that's it because that's what's gonna help you a lot. Is literally you have to write if you want to flip it. Don't write change the sign. Write down multiply it by -2. Because when you go back and you actually multiply everything out, you're not gonna remember to change the sign if you don't write negative somewhere. Right. So make sure you do that. Okay, that's gonna help out a lot.
Okay.
It's like mindless towards the end. So
I'm still getting it wrong.
Well, you did do that. You actually did flip it. You did flip it here. So you took this guy, flipped it, you made it that, and then you took this guy. What'd you do with this guy?
Oh, this guy? Oh,
I see where you're wrong.
what up?
This is where you're wrong. Here and here.
How am I wrong here?
Okay, so how does this all cancel out? This cancels out with that. Cool. Then exactly that's where you went on. So this guy cancels out with this, right? Cool. So now you're left with these 4 things right here. 1, 2, 3, 4. How do those cancel out? You didn't make them cancel out. So how many hydrochloric acids do you have here?
6.
Gas. How many do you have here?
1 gas.
Okay,
So
so
multiply that by 6.
exactly. Well, just to double check, how many hydrochloric acid aqueous do you have here?
6.
How many do you have here?
6.
No.
I mean 1.
Exactly. So both of these you multiply by 6. So you have to take this and multiply by 6.
Okay.
There you go. So you basically, that's good that you're getting all this, like, because like before, like the first time we worked on this, you were like trying to figure out like what would I write down here, but now you're basically just missing just that one little extra thing. Just multiply by -6 and just add that to whatever you had, and you should be able to get the answer.
Alrighty.
It's like, all right. I'll let you have a question.
Yeah.
Same thing.
Yeah.
Okay. Okay. So what is the partial pressure of? Okay. So you solved all this stuff. Let me do the reagent next. What is the partial pressure of H or NH3 gas after the reaction? PV equals. Wait, why'd you do PV? Is this a continuation of the other problem?
Yeah.
Yep, it is. Okay, so you got all these right, nice. Okay. So the entire system is that bubbling. Alright, so that produces NH3. So that's when the gas funnel is open. Okay, so how many moles did you figure out that that is? Either the H2 or the 2 regions. So that's how many moles of NH3 is there. As the R constant times that times divided by the 14. Oh. See, with this, you're assuming that the whole entire thing goes to completion.
Yeah.
Not exactly, because remember how you wrote his limiting reagent?
Yeah.
That means there's still excess N2, right? So you have to take that into account, which is actually what you did here. This is a big So you're saying that in this one, you're saying that all of the N2 reacted, but N2 didn't all react. So basically, you would have to go back in here and you have to figured out how many moles actually reacted. Right? Just curious, I don't know why this is I might be able to make it, but you basically take this mole and you figure out how many N2s are left. Right? You take that number of moles and you put that in here. But the problem is you need to figure out that the total pressure, the PT, equals the pressure of N2
25 halves.
right? Because you use the is what the H2 all of the H2. So the only pressures you have left is this guy. Using the limiting reagent, you can figure out the number of moles of this. The number of moles that are in this and number of moles of that, and you can use the equation P total equals pressure of N2 plus the pressure of N2. Okay. Yes. Okay. Yeah. So this one should actually be 0. Do you know why it's 0?
Because it's extra reaction.
Yeah, exactly. Because you said that H2 is a limiting reagent, so H2 is all gone. So that means the pressure of H2, if there's no H2, it's going to be 0. So that's why you have to write 0. Right?
How about the final?
The final is basically these two added together.
Oh.
I mean, they should have given. Wait, yeah. If you added these two values together, you would have gotten 8 points.
Okay.
But you added these two together. You want to add these two together. Okay. So that's why you have to think about. You really have to think about what's going on in the system in order to figure out the actual problem.
Wait, add these two together?
You add these two pressures together to get the total pressure, because you said that H2 is all consumed, it's all gone. Okay? So it's just this pressure plus that pressure equals the total pressure, which is these two pressures. But you did these two. Okay. Well, I'll come back to you on that. What's up?
Try number 14 and I'm having trouble with
14?
this.
Getting me a bit stuck. It is already. I would love to help, but my problem is I can help you out there. Right now, it's actually the end of our session, believe it or not.
Just need help on that one problem and then I